I'm going to start 9.2. Okay, let me open 9.2. Resistance and resistivity. Okay. So resistivity is kind of another property we need to discuss. And it's something that's very indicative of the material that you're working with. So, but let's go through some of these fill in the blanks here first, and then we'll talk more about resistivity. Okay, so the resistance of some material varies directly with the length of the wire, and inversely with the width or cross-sectional area of the wire. And the formula is right here. So R is going to be resistance, as we know, which we measure in ohms. L will be the length, which we'll measure in meters. A will be area, which we'll measure in meters squared. And this P thing here is called resistivity. And that's measured in ohms times meters. Resistivity doesn't change for material at a given temperature. It's kind of like boiling point or freezing point. Like, for example, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Unless if you start changing the air pressure, you know, like if you move to higher elevations, then that could change. But so resistivity is something that's very specific to material. So silver has a certain resistivity, copper has a certain resistivity. And you can see that all these here, all these metals here have very low resistivities, like silver has probably the lowest of all these, and then they tend to increase for other materials. So these are all good conductors. And semiconductors means they semi-conduct. So they're not as strong, but they do allow some electricity to pass through, but the resistivities are higher. And that impacts the resistance of the wire itself. Now, length matters too. So the longer the wire, the more resistance we'll see, because it's, you know, it takes longer for the, you know, the current to pass through. Area, if you have a very small area, you actually tend to see more resistance. So again, if you have a higher area, then of course, then you're not going to be as constricted with electricity flowing through. So if you have a short, thick wire, so thick meaning it's has a lot of area, and short, then you have very small resistance. So you don't want your wires to be too long. You like to have a lot of area. Like, you know, you want to like a wire that's kind of like pretty thick like this. But if you have a very thin wire, or kind of like my stylus, and it's long, then you're going to see a lot of resistance. Okay, P again stands for resistivity, and it's indicative of the material we're working with. And those are the units right there. Metals have a very small resistivity. Insulators, pretty large. And semiconductors are more medium. Silicon's a semiconductor, and that's used often for producing microchips, mainly because they won't overheat. So yes, you want to have good conductors, but something like copper will overheat. So semiconductors, like silicon's kind of like a nice in between. That's why we call the Bay Area Silicon Valley, because a lot of semiconductor companies started there and helped make the Bay Area famous for being a technology hub. So if we keep moving, any questions so far, or can I clear the screen? Okay, and I'm recording, just so you know. So I'll clear the screen. Okay, so why are long wires thick? Well, here we have wire thickness are measured in gauges. That's kind of a unit that sometimes people use. 20 gauge wire is thinner than a 16 gauge wire. The 20 gauge wire has that area, and 16 gauge wire has that area. Find the resistance per meter of each if they are copper. So remember, resistance is that. You can kind of move things around a little bit. So what I'm doing here is I'm simply multiplying both sides by 1 over L. So that's how I got this over here. And so resistance over length is what they're asking for, resistance per meter. So, and you're dealing with copper, which I have my screen here. It's 1.7. So we'll do it for a 16 gauge wire. And 20 gauge. I can't spell. Oh, hold on. So again, 1.7 times 10 to the -8. Divided by the area of a 16 gauge wire, which is 13. And the other one, you can use the same resistivity. Divided by its area, which is smaller. And if you were to compute that, for the 16 gauge wire, you would get 0.013. And that's an ohm per meter squared. And for the 20 gauge wire, you get 0.033. So 20 gauge wire, which is thinner, there's more resistance per unit area for 20 gauge. So you probably would imagine that a 16 gauge wire would probably be a little more expensive. Let's actually go online and take a look. See if I can see. you kind of see the prices there for 16 gauge. I don't know. Maybe I'm not sure what I'm talking about here with the prices. Let's not worry about that. But anyway, 16 gauge has less resistance. Okay, let's keep moving with actually resistivity and temperature. Yeah, we'll talk about a little bit. So there's a formula that can be used to determine the resistivity based upon what the temperature is. So P is the resistivity at a certain temperature, P0 is the resistivity at a different temperature. Alpha is some sort of coefficient that depends on the material you're dealing with. For metals, resistivity tends to increase with temperature, and alpha is positive. For semiconductors, they tend to decrease with temperature, and the alpha values are negative. And then we can kind of replace the P's with R's and kind of do the same thing. R's is a certain temperature, R0 is temperature T0, alpha again is a coefficient. So let's do a sample problem that deals with this stuff. Then we'll talk about superconductors and we'll have you guys try some problems after that. Okay. So heating element is a wire with a cross-section area of that is 1.3 meters long. The material's resistivity 4 times 10 to the fifth at 200 degrees Celsius, temperature coefficient. Find the resistance of the element at 350 degrees, which is usually what we're heating it up in, right? So what we first need to do, we know this formula, right? And we know the area, and we know the length, but we know P at a certain temperature. So I'm going to call this P0, and that as T0. And remember, we have this formula here that P equals P0, 1 plus alpha delta T. So P0 is going to be 4 times 10 to the negative fifth, 1 plus your alpha for negative 2, 3 times 10 to the negative 2. And the change in temperature is going to be 150 degrees. So remember, delta T is change in temperature, and that's going to be T right there. So we calculate the new resistivity, which looks like it's going to be, do this correctly here, 2.2 times 10 to the negative 4 ohm meter. And then we come back over here. Times the length, which is 1.3 meters, over the area, which is 2 times 10 to the negative 7th. And you should get, that's 1.3 meters, by the way. And the units are correct there. And I think it comes out to 1,430 ohms. And that's the resistance that we'll see in that oven. And then from there, you can use that to calculate the voltage and current and all that other stuff. So that's that calculation. You'll see some problems you'll work on that are like that. Let me clear that right now. Let's talk about superconductors really quickly, and then I'll have you guys do a little bit of practice. Superconductor. It's one whose resistivity is 0. So it's very good at conducting. So very good at conducting electricity. Resistivity is essentially 0. Metals can become superconductors at very low temperatures. Some materials using copper oxide work at much higher temperatures because sometimes you can't achieve those low temperatures. No current loss. Transmission of electricity, so it's used in transmission of electricity. MRI machines. I don't know what this is. If I see here in my notes, I'm not sure what machine that is. Look for power small locomotives, faster computer chips. But that's where we tend to see superconductors happening. So starting with number 4, if you're dealing with like copper, make sure you use the table above to get its resistivity, to calculate its resistance right there. And there's a bunch of other problems I'll have you guys try as well. So we'll just do, should go by pretty fast, 4 through 12. Give you guys about 10 minutes or so just to see how it goes. If we need more time to do this, we'll do this when we get back from the break. But go ahead and do 4 through 12 right now. And then we'll reconnect around 11:30ish, and then we'll take a lunch break after that. So again, 4 through 12, you go to your breakout room.